with a picture of a large 2-track monoboom on it, just to check everything's working?
I can indeed, thank you.
Perfect. Okay, let's go. Good afternoon, everybody. Obviously, this I see we're on about 290 people joined when I last looked, so it's obviously a little bit controversial, a little bit interesting. Oh, come on, work properly. There we go. So a quick agenda of what I'm going to go through today. I'm planning roughly to talk for about 40 minutes, and then we'll take questions at the end. We'll do a quick recap of Series 1 and the project, have a look at what the remit was and what the real priorities were, and what distracted us from that remit, because that has a big part to play in where it all went. I've got 3 case studies: the monobooms, the TTC, and the self-supporting anchors. Have a quick look at allocation design and what we did to try and get the best out of the structures there. Look at people's state of mind, why the structures seem to be so big, and what's happening with them now, and what lessons are there really. So that's what I'm going to run through. A quick overview of me. Hopefully a lot of people have met me before. I'm a chartered mechanical engineer. I'm not civils, I'm not structural, but I have people work for me who that is their specialism, and I have a good grasp of what they're doing, but I am mechanical. I'm in my 24th year in rail now. I did 4 years or so in Balfour Beatty, 12 years or so in Network Rail, mixture of maintenance and overhead line projects, and I'm engineering director with Furr and Frey GB in almost my 11 years now, yeah. And my assumptions for today, being quite blunt, this is, I realise there's a lot of people, but it's kind of a fireside friendly talk. It's me sharing my technical knowledge, my experience from the Great Western and Series 1 project. It's my personal opinion, my personal experience. It's not a corporate opinion. And some of the numbers I'm going to share are hard numbers that I've taken off drawings. Some of my best guesses, just to make it easily for discussion today. And please, things that I say today, if you work in the media, if you're going to share things that I say today, please make sure you're competent to share them. Don't just take a sound bite and share it, because it might be completely out of context. One of the issues with Great Western is you really need to understand what's gone on to really be able to talk about it. And hence today, hopefully, will get us all a little bit closer to understanding what's gone on. So that takes me quite nicely into looking at what were the priorities in 2012, 2013 when I joined. Great Western electrification, they had a new fleet of trains coming, mostly EMUs, a few bimodes to help through the transition. And really, above everything else, the priority was get electrified Paddington to Swansea and entry into service by 2017. When I joined in 2013, that was king. And that was going to be achieved by high output plant construction methods. And they were the 2 biggest priorities really for the project, followed by making sure they've got to Swansea by 2017 using high output plant. That was the next biggest priority, followed by making sure they got to Swansea by 2017 using high output plant. You're getting the theme. It was all about meeting those dates and that methodology. Then there was cost. And then there were some other things that now we think are important, but probably weren't on the radar quite so much at the time. So just keep that in mind. The priority was getting to Swansea by 2017. And back in the sort of early to middle parts of the project, there were over 1,000 staff working on that project, and the run rate for the job was roughly £5 million a week, which is about £2 a minute if you look at a 40-hour week, being spent on overheads, design, project management, safety cases, that kind of thing. This isn't the people on the ground building, this is the project overheads. So it was really, really clear. And that's not a criticism, by the way, that's a reasonable amount of money for such a huge project to deliver such a huge goal. But the priority was all about speed. I've laid the numbers a little bit. Very roughly, I reckon steel was costing about £700 a tonne back then. So in terms of the cost of steel, the overheads for that project were costing 3 tonnes a minute of steel. Just remember that as a figure, quite interesting. So back into the technical, Series 1 as an overhead line system. We were asked to provide a 140 mile an hour system that would work with multiple pantographs. The feeding was auto-transformer feeding with an earth wire. We had to show a step change improvement in reliability. We had to be TSI compliant, European interoperability. We had to show improvements in safety. We had to show less maintenance, and we had to have, this was new, 120-year structure life with minimal interventions. We had to do high output construction, as we know, and we were looking at high output design. And one of the big takeaways was we wanted, from lessons learned off the headspans on East Coast Main Line, we wanted proper mechanically independent wire runs, no tail wires threading through each other, purely one wire run is connected to an anchor, and if that anchor or that wire run fails, it doesn't take other things with it. We were also looking at safety by design, and that was seen by the project as doing your site works were all mechanized, your hand work was assembly off-site. So you were minimizing your time on site, and what you did do on site, you were maximizing use of machines. And procurement, the idea was make it as simple as you can, a kind of a one-size-fits-all approach. Now, really simplistically, if you strictly follow one-size-fits-all, it has to be the biggest. You're going to only have one size, it fits everything, it's going to be the biggest, it's going to be the heaviest. So obviously we didn't go fully down a one-size-fits-all, but that was the original mindset, to make procurement for this huge job quicker and easier. Early days, there were a lot of distractions, so you don't need to read the details of this table, this chart here, don't worry. But this is the inputs chart, or the interfaces chart, for the Series 1 system design. And the red circle there, that shows the elements to do with structures. So overhead line structures were actually a pretty small part of the whole job. And as we were developing the system, 2012, 13, 14, 15, at the same time, Atkins and several other teams were busy doing allocation design of that ever-evolving system. So there's a little bit of chicken and egg going on, and there was an awful lot going on at the time. I realise, like, I'm setting excuses here before I go into the detail. It's not the intention. The intention is just so people understand the project mindset at the time. And the priority was get the piles in the ground. It was the right priority. But we had a lot of unknowns at the time. So the line speed, I said the remit's 140 mile an hour, multiple pans. We probably all know Great Western is 125 miles an hour, but overhead line lasts a long time. There was a sensible aspiration for 140 miles an hour. That has a massive effect on the tension and or the wire size, the system heights. There was a lot of discussion over overspeed. Is 125 plus 10% what you need to do? Well, that's about 138 miles an hour. If you go for 140, you don't need as much overspeed because you would use better signaling. It to and fro and to and fro. And we ended up, originally the tension was 16 in the contact, 16 in the catenary. For a while it was down to 15, 12, and then some simulation work, it settled at 16 and a half, 13. But all the early works were based on 1616. We then had, for those of us who are electrification engineers, hopefully most of us in the call, we had 1210 came along, and that was mandating new wire heights, especially around level crossings. So these changeable loads are going in at changeable heights. We also had issues with wind speed. So PAN 72 that we know and love now didn't exist. That defines the wind speeds. Sorry, Civ 72, Civ 73 didn't exist, and also PAN 97, the wind speeds pre-new standard, didn't exist. So we made our own wind codes, but everything at the time was designed for 37 meters per second ultimate limit state. So it's quite high wind speeds, and that affects the size of the mast, the size of the base plates. That affects what span lengths we can do. There was all sorts of things going on that changed the load inputs. We then started doing some dynamic simulation. So Network Rail wanted to maximize the resilience of Series 1, making sure that it could stand certain defects like droppers off or high winds, and not suffer degraded performance. So that affected tension, mass deflection, wire sizes, system heights, all these things added up to affect loads. We had TSI compliance. That generated a lot of conversations. What does a nominal 4.7 wire height mean? I'm going to leave those there, but it was changing loads and it was changing heights. Electrical safety, we hadn't done a lot of auto transformer work in those days, so there was a lot of discussion. How much clearance do you need? How high above the wires does the auto transformer go? And do we have dangler supports that allow a long track movement, or do we have fixed posts that put torsion in the masts? So again, loads and heights were changing. We also had crash safety. So after Hatfield, there were some reports done looking at the effect on a derailed train of overhead line structures. It was quite controversial at the time, and whether it was accepted or not was an interesting state of mind. But certainly the safety case got us to temporarily redesign structures from H sections and square sections to look at the cost of going to oval sections because they were better in a crash. We saw sense, we all went back to normal sections, but again, that changes loads, wind loads, added quite a bit of time. HOPS, high output plant system, excellent train, much complained about, but it was a very good piece of plant in its infancy at the time. The ORR were very interested in how we treated things from a safety point of view, how we were going to carry materials, what was a safe working zone, even which track was the train going to work from. And this affected the lengths of the masts, the height the wires were going to go at, things like walk out of structures. It all affects heights and loads. We had the Eurocodes. They were mandatory, I think, from 2010. Everything had to be designed to the new civils Eurocodes. So lots of civil engineers were arguing with each other about what safety factors we should use. So that affected loads. So all of these things, by about 2015, 2016, they were all sorted. They were all agreed. So we went back through Series 1. We did some value engineering. We changed the allocation tables that you'll see later and made Series 1 a good chunk more efficient to meet the actual loads it had to withstand. But by then, a good half of the design and a good quarter of the build had already been done. So quite interesting early days. That's the history. Let's jump into just a quick reminder of the structures themselves. Apologies, most of my photos are either of things that were wrong or things that were being built. I don't have many good pictures of things that are finished. Hence, this photo here has no ATF wire yet, but this is a fairly standard single track cantilever, HEB H section masts between 200 and 260 millimeters. And this particular one is really tall. The ATF feeder, at the time there was a 2 meter rule. It had to be 2 meters higher than the catenary to let one be on while the other was off. I think that rule has gone now, but that meant we had quite tall masts which catch the wind more and end up being slightly larger. Reasonable things done for safety, but it was pushing bigger masts. That's your standard STC. TTCs, two-track cantilevers, really common on the route, quite innovative. I'm going to talk about these later in one of my case studies, so I'll move along. Q-booms, wherever the TTCs were too short to get across 6-track areas or wide 4-track areas, we went with our Q-booms. These are slightly larger than people are used to because they're land and leave. That means they're much faster to build, but the way the loads flow between the mast and the boom puts more load on the boom. So the booms are a little bit chunkier than people would be used to, but much quicker to build. We then had portal style midpoint anchors. I don't have a good photo, I'm afraid, but the idea is the catenary there anchors back to back. They're not that common, these structures, reasonably efficient. So it's just for reference that they exist, really. I'm not going to go into them in detail today. We then have the big daddy. We have the monoboom. Everybody's seen these around. You cannot miss them. I think these are a good bit of why people think the structures are so big, and we'll talk about those in a case study in a minute or so. We also have SSAs, self-supporting anchors. This is where you have an anchor structure with full wire tension on it. The photo is from Old Dolby test track with balance weights hanging on it, not true Series 1. And it has one of my slimmest members of staff standing next to it. But these are a 350 by 350 square hollow section steel mast, similar size to the OLME ones. But let's jump into the case studies. So that's the background. Monoboom anchor portals, these are the big ones. It was all about this remit of mechanical independence and not having tail wires threading through other equipment. So I'll run you through some examples now. We'll look at Mark IIIB, which is really common in the UK, very efficient design from the 70s and 80s. I'm not going to talk through the Heathrow portal, for those that know that. It's got a big list of problems why it just isn't appropriate for this use. I'll then show you most of Europe, and we'll have a look at Series 1. So into Mark IIIB, very common on East Coast Main Line. This particular drawing example here is from Midland Main Line. The idea of this, looking at the center two tracks here. Come on, mouse. The center two tracks here. So your overlap is in the middle, and your anchor wire here has to thread through the outer wires and go out to anchor in the cess. The problem you can see here instantly, this whole arrangement is 300 meters long, just to support a 50-meter overlap in the middle. If I zoom into a schematic here, so let's take this dotted line here. This is a wire that's been running for a mile or so, goes through the overlap in the middle. It ends here, it goes out of running, but we have to cross it with an insulator into the headspan, so it's now electrically the same section as the outer track. Cross it through that, another insulator, then we take it off to anchor in the cess. So whatever plant or machinery you've got in the middle track here, you also have to either get a long reach on it or you have to get some other plant out in the cess to anchor it for you. You've got to thread it through between these wires. It's a right pain. It takes time. That's called flaking. If you hear me talk about flaking, that's passing one wire through the other simplistically. So you've got lots of components. You've got lots of overlap here. You've got 300 meters where 50 would do. You've got a lot of work. And if one of these middle wires fails, it's going to take out the outer wire as well. So this is why we have issues on East Coast Main Line. If something goes wrong, everything tends to go wrong. So these were categorically banned for Great Western, and rightly so, to get good reliability. The rest of Europe, they do portal anchors or boom anchors directly above the track where they can in 4-track areas. So straight away, this is a single span overlap from our GEF system in Anglia. The 2 wires are only overlapping here for a single span, 61 meters in this case. There are 3-span versions, but we'll focus on the single for today. So that means you don't have any of this threading through. You don't have anything going out to the cess for the middle roads. Showing you a photograph of it is quite hard to explain, but simplistically, your anchoring wire, your catenaries go 1, 2, 3, 4, anchoring onto the top boom here. So each of those is roughly a ton of tension. And then your contacts, 1, 2, 3, 4, are anchoring on the lower boom. So this means your anchors are directly above the track. You're not worried about getting out to the cess, and whatever plant you've got on the middle road only has to work on the middle road. So we're beginning to get high output. But your 2 wires that are going to run off into the distance, one of them here has to go underneath the boom. That's nice and easy. But your catenaries for the non-anchor have to be posted through this letterbox that we've created and flaked through, which you just can't mechanize that. You have to do it by hand. So it's not very efficient, but you do have mechanical independence. We are anchored above the 4 foot. They're a bit slow. There's a lot of stuff to put up there, and we designed these specifically based on European practice. They're based on having concrete foundations as a rule. You've got a little ladder tie or strut here. Being a ladder is not good, but they were there to take these loads, the long track loads, down into the ground. And what you see with this boom, it's mostly loaded in bending. So it's fairly efficient to design a piece of steel to resist bending. If we now jump across to the monoboom, it's quite a different mindset, but it's fixing the exact same problem as the twin boom we just looked at. So your catenaries, 1, 2, 3, 4, are anchoring up here. Your contacts are anchoring 1, 2, 3, 4 on the Tensor X down here. And you don't have that lower boom getting in the way, so you don't have to flake or thread the wires through. And it's also much easier in some ways to install because you don't have the 2 different booms to put on there. But what you end up is full mechanical independence. You're not having to flake through, so you're high output compatible. You've got your anchors directly above the 4 foot that you're working on, so you're high output compatible. And it was specified for the circular hollow section piles like Great Western, again, high output compatible. And you're using the single span overlaps, which we showed in the previous slide. That saves you something like 5 or 10% at every overlap. So that means you need 5 or 10% fewer overlaps. And these structures are where the overlaps are, and that's where the money is. So the whole idea of a single span is saving you quite a bit of money. If we take a look from the left where that arrow is there, oh, actually, my final point on these are the ones, they look big and heavy, and I'll put my hands up. These monobooms, they are big and they are heavy. It's a fact, but you're hopefully going to understand in the next 2 minutes why that is okay. So if you imagine you're up a ladder looking from this orange arrow here, looking from the side, this is roughly what you're going to see. So we've got the 2 Tensor X's and we've got the anchor boom itself running through the middle here. So I'm going to talk you through the loads that are on these. So firstly, the orange arrow at the bottom, that is the anchor tension from the contact wire. We've then got the anchor tension at the top from the catenary. We've got the weight of this tubular frame with the Tensor X's on. We've then got the weight of the catenary that through runs. We've got the radial load of the contact wire that's through running. And we've got the weight of the boom itself, the infamous big boom. That's all fairly standard loads. The real difference we've got here is this blue dimension here. This is the mechanical offset where the contact wire is a couple of meters lower from the middle of the boom than the catenary wire. So this is putting a lot of torsion into that boom. And designing steel to not deflect and be strong in torsion is quite complex. And that's why you can see all these diagonal struts inside to stiffen that boom up. So that's the load it's taking, lots of torsion, as well as all the bending from the anchor loads. So we get a lot of criticism. I think it's a thing that people complained to me the most about Series 1 being big is these struts here, the anchor struts in compression. So they keep saying, why do you use these really expensive struts? Surely you could just use a nice cheap tie. Well, I'm going to explain to you why we can't use a nice cheap tie. So if you look at the loads involved, you've got on the contact wire here, 4-track, typical example, and I've just made these numbers up, they're top of my head, typical numbers. You've got 16.5 kilonewtons times 4. You've got 13 lots of catenary, sorry, 13 kilonewtons of catenary times 4, plus you've got about 12 kilonewtons of wind load. So you've got something like 13 tons of a long track load. You've then got the self weight of everything. You've got the boom itself is about 7.5 tons. And people criticize that. Whether it's 2 tons or 10 tons, you still need a crane. It doesn't make a huge difference. You still need a crane. We've got the tensor axes, we've got the small part steelwork, about 2.5, maybe 3 tons. These are all there holding up the wires themselves, which are in the realms of a ton when you put the cantilevers on. You've got the masts themselves, about 4 tons. So you've got a long track load of 13 tons, a vertical load here of about 15 tons. Let's put in this blue line, a nice cheap tie, like everybody keeps asking about, to resist those long track forces. Well, that ends up with about 19 kilonewtons in it. And the way these forces resolve, to resist that along track force with a tie, you end up with roughly the same downwards force as a result of the along track force. So you add that 13 tons to the 15 tons self weight, suddenly we've got 28 tons here of vertical load. And anybody who knows about piles will know that piles do not like vertical load. They're very strong in bending, in rotation, or overturning. But vertical loads, end bearing like this, they're really very poor at. And we were being told this is borderline impossible to construct. So to get more capacity out of a pile, you have to drill the soil out of the middle of it, and you have to backfill it with concrete, which is a real pain. Or you just ditch the pile altogether and go with concrete, and neither of those things are high output compatible. Just to get a feel for those loads, if you're into cars, this is a lovely, nice new Ferrari Roma. I'm sure we'd all like one. 28 tons is a lot of Ferrari Romas. It's 18 Ferrari Romas sitting on top of these piles. So that's a lot of steelwork, a lot of weight pressing down. If you're like me into mountain biking, this is a lovely Trek Super Caliber lightweight mountain bike. It's 2,600 mountain bikes are pushing down on there. It's a huge, huge load. So let's get rid of the really cheap, sensible tie, and let's use what I've heard described as the massively over-engineered strut. In fact, it's bigger than some masts. Well, yeah, it is bigger than some masts. It's not massively over-engineered. This strut goes in compression, so that means all that tension load, that 13 tons that was pushing downwards, well, that now pushes upwards. So you've got your 15-ton self-weight minus 13 tons of tension-related weight. So now your downward load on that pile is 2 tons. That's really easy within what a pile can take. And just to put it back in context, this is now the Ferrari Roma that I'd like to have. This is the right number to have. And maybe 1, maybe 2 mountain bikes, that's a good number to have as well. So by spending 1 to 2,000 on this massively over-engineered, bigger than some masts strut, we've saved thousands and thousands of pounds and many, many hours of piling. It's just clearly the right thing to do. So the cheap tie, you have a deep pile, it probably needs concrete. You get a big risk of it refusing. The bigger the pile, the more likely it is to refuse. You're going to get fewer piles per shift. You're going to annoy your neighbours because you're piling for hours to get these huge things in. And quite often it's just impossible. And these are all the downsides you would get by swapping to what people think is a cheap tie. And that is in no way at all high output. You go to the over-engineered strut, you can have smaller piles, lower risk. You're back into normal numbers of piles per shift. So you're high output. You've got less noise and you should have no concrete. So that's one really simple example of why what people see with their eyes as being massive and over-engineered, yeah, it's big, but it is not over-engineered. It's allowing you to get rapid installation, allowing you to work with the wiring train above the 4 foot, nothing goes in the cess, and you've got much, much, much smaller piles. And that's the mindset of Series 1. However, this is a photo I took at Old Dolby Test Track. And this is when I began to realize I might get some grief over these. So this is a 2-track monoboom with 1 equipment anchored on it. And it's on the same size masts as a 4-track anchor boom that could have gone up to 24 meters. And I just realized this is too big. We might want one size fits all, but this is just too big. So this is one of the things that prompted the value engineering. We went back and we said, look, you want one size fits all, but we need a big and a small, maybe also a medium. So the 2 tracks now were re-engineered to have significantly smaller masts, but there are still a few of these built, and this is often what people see. It was the stuff that was done early for the right reasons, but is seen as over big. So that was procurement a little bit. Case study number 2, TTCs. Remember that remit, we've got to get to Swansea by 2017. Everybody thinks portals are better, cheaper, more efficient, and yeah, they are. But you need all track access, and you only get that a couple of for less than 2 hours midweek, or you're stuck with Saturday nights. We've got land and leave portals, they're much faster to build, but you're still stuck doing these Saturday nights. It just doesn't work if you want to get there by 2017. Hence, we've got the TTCs. The whole idea of the TTCs is the boom is as short as possible, so you can install that boom with just a 2-line block. So that means you can be getting access every night of the week, 4, 5, 6 hours every night, and be getting these in. I'm going to play a little video now, which the sound should share. Simon, if the sound doesn't work, give me a shout.
Will do.
Midnight on the Reading to Paddington line. While the last trains of the day speed past, teams are working on the biggest upgrade project the region has ever seen. This is one of 4 trains that allow work to be carried out next to tracks that are live, meaning only a partial closure of the network. Tonight the teams are piecing together gantries that will carry the wires for the new generation of electric trains.
We can have live passenger and freight trains running at the same time as we are out here installing the new infrastructure. It's unique to this system, which is the Network Rail's high output plant system.
And we can see the guys are working, but we've got a train coming right now.
Absolutely, this is the live environment. You see it as it is. And our guys are out here every day of the week.
So that, I think, is a great video. That is proof they really were installing TTCs while they had trains on the other lines going past at 125 miles an hour. And that is exactly what the TTC approach. Yes, they look bigger. Yes, they look less efficient, but it's letting you do 10, 20, 30 a night on midweek nights instead of just 5, at best 10 just at weekends. So looking at the TTCs, a bit of economics of the mast. So the one on the left here is a standard UK OLEMI British Rail Mark III 2-track cantilever. Just looking at the mast, 8 meters tall. It's a 381 by 102 millimeters. The one on the right is the Series 1 equivalent. It's a 350 millimeter with a 12.5 mil wall thickness. And neither of these are tall enough or designed to take an ATF feeder, by the way, but their load capacity, give or take, is the same. So they're doing the same job, same sort of size. The one on the left, the OLEMI, weighs about 1.2 tons. The one on the right, the Series 1, weighs about 1.2 tons. There's nothing in it. The costs, so this is 2017 costs when I last had a quote. The OLEMI one on the left was 2,800. The Series 1 on the right was 2,100. I believe since Brexit that swapped around. But the headline for me, I'm not arguing over pounds and pence. They cost about the same. They weigh about the same. They're the same order of magnitude. The one on the right looks bigger because it's slab-sided and your brain sees the slab. The one on the left is broken up a little bit and your brain sees the aesthetics being a little bit smoother. It's psychological rather than fact. The one on the left is actually bigger and it's actually heavier. It just doesn't matter. They're about the same, really. But the big takeaway, the OLEMI one on the left, is 28 hours of fillet welding to make that mast. The Series 1, because it's a standard section, chopped and welded at the bottom, and pre-cut pieces welded on at the top, they were being knocked out in 8 hours each. And that really matters. Remember that remit, down to Swansea by 2017, there's something like 3,000 TTCs. I've had estimates between 2,000 and 4,000, but of the people I've spoken to, 3,000 seems about right. If you've got to make 3,000 TTC masts, that's 15 working years just to make the Series 1 style masts at 8 hours each. If you're going to make the OLEMI ones, which people think are more efficient, that's 52 working years for a person in a fabrication shop. And Network Rail procurement teams, they went to the UK steel fabrication industry and there just was not the capacity to make what they wanted. Hence, we went to these larger sections, just chopped and welded, because of these economies of scale you can see here. They're just the pure efficiency in getting more made. This is only the masts, it's only the TTCs. So it's only perhaps a fifth or a tenth of the structural steelwork required for the whole job. So yes, they're a bit chunkier because they're faster to make. Absolute no-brainer for this project. You've got on the right here, this is a Mark I TTC, that as a piece of engineering, it's much better, it's more efficient, it's leaner. But this was designed in the 60s when labour was cheap and materials were really expensive. So they were happy to spend the time welding those up. That just would not work for Great Western. Whereas now it's the opposite way around. Labour is expensive, time was critical for the project, and materials in the scheme of it were relatively cheap. So as a mindset, it was all about the high output. It wasn't focusing on saving steel. However, it wasn't, this particular example, which I picked at random, wasn't any heavier anyway. That's the manufacturing. You've then got the installation economics of it. So passing the boom to the mast with an OLME TTC like this, a good team can do that in about half an hour. If you're not such a good team, probably more like an hour. And your crane is tied up for that entire time. So you can't do many of these in a night. The TTC on the right, the Series 1, land and leave, high output, that takes 2 minutes to put the boom onto the mast. I'll show you this little video. There's no sound with this. So this was our prototype, ungalvanized. This was the first time we'd done it. And it actually took longer to sling the boom onto the crane than it does to land the boom onto the mast. So you tilt it up a bit here, you hook it onto the hooks at the front, and there's a little pin at the back. We use gravity as our friend, so its own weight joins into the pin at the back and locks itself in place like this. And that's it installed. You have a separate team can come along later and drop a safety pin in at the back that isn't in this video, just to make sure it doesn't come out the same way by accident. But this is the whole point. Rapid construction, land and leave. These things are less than 2 minutes each. When you do the maths, the Ferrari's there again on the level crossing. He's got away from the monoboom. 3,000 TTCs, you're working on midweek night shifts. You've got 2-track access here, 5 or 6 hours if you're lucky. Just to put those booms on those masts with the OLME type, you're looking between 500 and 1,000 shifts. To do that with the Series 1 type, they genuinely were doing 30 of these some nights. If they had 30 on the train, you could do the lot in 100 shifts. So the productivity benefits from these different styled masts was enormous. And that is all there to get that remit of getting high output plant and getting it wired by 2017. That was the mindset behind it all. Third study, super quick, SSAs, self-supporting anchors. Most people just don't like these. You look at them, they just look like they're asking for trouble. But when you do the maths, it's an absolute no-brainer. The mast itself, a Series 1 SSA here, it's a 350 by 16 millimeter wall thickness. Compare that to the OLME equivalent you would need for the same. That was a 356 by 368. It's the same, they're the same order of magnitude. But you have this slightly more expensive mast, but you don't need a back tie on it, and you don't need the second foundation. So you've got one expensive mast, one expensive foundation, instead of one medium mast and 2 medium foundations and a tie. And when you add that up on materials alone, these are cheaper. But then when you add in that you don't need to do 2 piles, risk of refusals, noise for neighbours, all that kind of thing, again, it's an absolute no-brainer to use self-supporting anchors wherever you can. And this is quite a big looking structure, but we had this approach of one size fits all. So this had to take the anchor loads at a level crossing where you're anchoring at sort of 7.5 meters. And because it's the plain square sided, we realized afterwards, they do look bigger on your eye because they're slab side, no shadows. But from an actual size point of view, it's no bigger than the OLME equivalent. We do have an asterisk at the bottom there. There is the large 500 by 300, and that's if you're having to put the pile at the bottom of an embankment, say, or if you're anchoring the ATF as well, where you've got really, really abnormally high loads, but they're quite rare. So yeah, SSAs, it's all about getting one pile in with one structure instead of needing 2 piles. So that's a quick run through of some of the case studies with actual loads. We also have the mindset of high output allocation design. So people who've designed in the past, if you've been allocating structures, I always found it really, really difficult allocating OLEMI structures, the summary of calcs weren't very user friendly. So we produced these allocation charts for Series 1. And the whole idea is you don't need much competence. As long as you know how many wires, how many meters, you can very quickly work out what the right structure is. So this was all about feeding the factory, high output design for high output construction. But everything has to be rounded up a little bit. So we made these tables, we revised them completely in 2016 once all the parameters were set. But the whole mindset here is to let you quickly work out your structure types. So a typical example, if you're doing a portal, you've got a 17-meter span, you've got 7 or 8 equipments on it, and your top of the pile is less than half a meter below the track. Straight away, you look across to these, that tells you it's a Q100 boom. You can have the small mast, the 250 mast, with the thin wall, the 12.5 mil wall thickness, and you can drop it on a 610 pile. That takes seconds to allocate a structure instead of potentially quite a bit longer, working out all these different variants in the OLEMI style. Maybe less efficient on the steelwork, but weeks faster on the program for design times. That's high output design. There was also high output procurement, and this is a photograph, thanks to Google, of the A420 as you're coming into Swindon. And every time I drive down this road, it just makes me feel a bit embarrassed. So Network Rail, for good reason, bought a lot of structures in advance. There was some sort of mistake, I don't know the details, but there ended up being 1,000 structures ordered by mistake. And they were sat in a field somewhere trying to achieve this 2017 deadline. It was the right thing to try and do in good faith. But you look at this structure over here, this is a single track cantilever with not much load on it. It's got the ATF further up, but for some reason, this is a 350 by 350 structure, far, far bigger than it needs to be. But I know Atkins were instructed to use these because they were spare. They've been bought by mistake. Yes, it looks not ideal at all, but it's much better to use your scrap than to scrap your scrap and then buy the right structure. So I think there are lessons for procurement there. It's all about what risks you take to try and get things. They'll have bought a lot and got them at a good price. But there's quite a few of these on the route where you stand and look and you think that structure's too big. And yes, it is too big, but effectively the structure was free because it was spare. It was from a field. You would always use something that was spare rather than design the right thing. I know some of the designers were tearing their hair out because their name was on the design, and I accept that. So it was the right thing to do to resolve another mistake. But yeah, that is a good reason why you see some of these larger structures. Hopefully that makes sense. So what's happening now? Middle Mainline, they are using 2 and 4 track monobooms. They're using F-boom midpoint anchors. Transpennine, they're using, I'm told, hundreds of TTCs because of the constructability benefits that they can get them built quick. They're also using 2 and 4 track monobooms. Shenfield, Southend, Victoria, they are finished now. They're using TTCs, monobooms, and F-boom midpoint anchors. Crossrail, East and West, they took the monobooms and have been using those as well during Crossrail. Scotland, they're using monoboom anchors. I've seen some at Carstairs Junction remodelling recently. And Transport for Wales, they're using Q-booms, TTCs, and F-booms. And Anglia Mark 1, we used TTCs and self-supporting F-booms there as well. So converting the F-boom to self-supporting saved us 4 foundations for each one we did. Huge, huge savings, but they're a little bit bigger to look at. So that to me shows that the industry has seen the benefits and is actually quite liking the benefits they give you. What else is happening now? Well, our competitors are trying to make copies. There are other attempts at TTCs and monobooms. I'm taking that as a big compliment. People can see that, that it's the right thing to do. The F-boom midpoint anchor, the TTCs and the monoboom, they're in UKMS now. And just a reminder to people, the licensing for these structures, Network Rail and us have joint rights to the structures design, so anybody can use them in the UK for Network Rail. Although outside the UK or outside Network Rail, we do own the design rights to them, so no one should be allocating these without our permission. But come and talk to us. That permission will not be withheld for any reason, any unreasonable reason. We're not looking to make money out of structures. It's not what we're here for. Last point, have a think. What do people see? What's the perception of these structures? you see what you can see today now. You see the height of them, you see the width of them. Yep, they're tall, yep, they're wide. It's for good, real reasons. You see big anchor struts. Well, hopefully now you understand why those big anchor struts are there. They're giving massive savings under the ground that you can't see. Those big anchor booms, yep, they've got torsion in them. That makes them need to be big, but that made the wiring so much quicker and safer. The aesthetics, yeah, you can see that they are what they are. That's just a fact. But hopefully from this quick run through it, you can see some sense, some commercial sense as to why we did this. What you can't see the past, you can't see the decisions, you can't see the wall thicknesses. Some of these structures have quite thin walls. You can't see the pile depths that aren't there because we've made the saving. You can't see the hundreds and hundreds of piles not needed because we converted things to be self-supporting. You can't see the flaking that hasn't had to be done. You can't see the shorter possessions, and you can't see the time saved within those possessions. It's really interesting. People just see the big stuff and think it's bad, when actually it's given massive benefits. So a little reminder, the remit was all about getting it built quickly to be down to Swansea for 2017. And Simon Skinner, engineering director at SPL, he quoted in the PWI electrification event in Sheffield, Series 1's actually not that bad. I'll take that. He understands what's going on and he's using Series 1. So yeah, the structures are bigger than we're used to for good reasons, but they're not unreasonably heavy. They're doing a bigger job. They're taking bigger loads. They're comparable sizes to OLEMI. They're just taking bigger loads. They're not over-engineered. Yes, they're large. Yes, some of them are heavier, but they're not over-engineered. They're there to meet a remit of quick and easy fabrication, quick and easy construction. And they have, I think, delivered their remit of high output, fast construction. Otherwise, those other projects wouldn't be using them on their jobs. It's saved a huge amount of unseen cost and time. And I think the additional steel is pretty much trivial versus the benefits. And I do worry sometimes the industry forgets that. We maybe have known, but we forget. So my final reflection, what do I wish? Sometimes I wish we just hadn't made such big structures. It embarrasses me, but I know it was for the right reasons. Therefore, I actually feel proud. We have done the right thing for the right reasons and the benefits were there. It's just people only see big structures. What do I hope? I hope all you people on the call today have hopefully got a little bit closer to understanding it, understand the examples, and I hope you share those benefits with other people and keep using them. Anybody can blame big structures. It's easy to blame big structures and say electrification is rubbish. We all have a duty to look at the engineering and get electrification cheaper so we can have more electrification. And sometimes big structures, they actually help the electrification a huge amount. So future electrification, the real cost, I think, is not in the steel. It's about project management. You've got to minimize change. You've got to minimize innovation in the middle of a project. Get your value engineering, get your parameters, get that agreed at the start, and then your project will run smoothly. And my lesson is Series 1 structures, yep, they're large, but they've freed up huge amounts of efficient, unseen electrification. And that is me. Any questions? Simon, I think you're going to chair.
Thanks, Rob. That was really good. You want to get a glass of water after all that? So
I'm ready.
Right. Okay. We've had quite a few questions. I'd got one prepared, but I'm happy to speak to you about that afterwards. For me, a lot of people are coming up.
Yeah, I'm also happy to stay on
users.
afterwards and take some questions.
Okay. A lot of people are coming up as unknown users, so apologies for that. So if I've got someone's name, I'll ask them to come off mute and ask you the question. If I've got you down as unknown user, I'll ask it for you if that's all right. However, I'll go through chronologically of how they came up through the chat. I think it was Michael Ziedler had a query about the HOP system. But I think that was more regarding where has it worked since Great Western Railway. So I think it was slightly outside of your remit.
Yeah, I've got no idea. It went over to Anglia and was being used in Anglia. Where it is now, I don't know.
I think the HOPS train. I think some of it is still in Swindon, such as the foundation part of it and the steelwork. I think the wiring unit went to the high output team. So there was a query about what's FNF's thoughts on the legacy 1111 kilonewton systems, providing acceptable current collection for 2 and 3 pan operation. at 110, 125 on East Coast Main Line and well, it's Great Western Main Line. I don't know if you've got any comments you'd like to have that.
I don't have it. I guess my thoughts on it don't really matter. The data should speak for itself. 1111, when it's run through systems like our Picada or the other simulation systems, it seems like it certainly can perform a little bit. It can perform with a slightly more onerous load case than it was doing on East Coast Main Line. I know it's running at higher speeds with more pans now, and that's good news. The lower tension you can have, the better, really. Yeah, I'm all for it. You don't need high tensions necessarily for high speeds, but you've got to simulate it, and the math speaks for itself.
Yeah,
I think we'd all take lower tensions if we can.
Yeah. Okay.
It depends on. Oh, sorry, go on.
No, that's right.
I say it depends on other factors, doesn't it? You get more blow off. So just because somebody thinks lower tension is better for one thing, you might end up with shorter spans because you've got more blow off. We're doing some work on that at the moment with Network Rail, which will be publicising the results shortly.
Yeah. Okay. Do you know if the project fed into the development of Civ 72, 73 and any other standards? I think they probably did.
So Civ 72 and Civ 73 was work in progress when we started. There was a pan that kind of covered some of the civils assumptions. I'm going to stab a guess that Civ 72 and 3 came out in about 14, 15. So that we didn't feed directly into that. We weren't responsible for the foundation side. We were just doing the structures. But then we used, I think, draft elements of Civ 72 when we did the value engineering. We have since been involved with Civ 72 and 73, but no, Series 1 and Civ 72, I would say, were pretty much disconnected. It was all about Eurocodes back in those days. And Civ 72 or 3 was the Network Rail approach to covering Eurocodes.
Gary says Civ 72, 3, 4 was 2015, so you're okay. I think you're quite close. Sam Jones has got a comment. This is the first one I'm really recognising. If Sam would like to come off mute and ask his question.
Thanks, Simon. Thanks, Rob. Really enjoyable presentation. I'm going to be cheeky and I'm going to ask 2 questions. And I'm also going to advise that in your presentation, you said that land and leave was done on Saturday nights. We did actually manage to do midweek nights as well by taking line blockages for 20 minutes just to do that land and leave. So again, we as the project progressed, we did get more efficient with that as well.
Yeah.
So I'll read my questions. So F&F, obviously, you were designing in accordance with the remit and the scope that you've been given for Series 1. Knowing what you know now, though, and also with some of the work that you've been doing, developing composite masts and things like that, what would you do differently, or would you do any particular changes if you were to do this again?
I think we had this one-size-fits-all mentality for the easy procurement. And I get that when you're building a factory, it's not just the hops train is the factory, it's design, build, procurement, everything has to be quick. Because if you've got anything that's slow, the whole system drags down to the slowest. So I support the approach of the one size fits all, but I personally would have a few more increments. I don't think it would cost that much more procurement time to have a few more increments. So you didn't always have to round so far up, if that makes sense. A bit like the masts on the monoboom there, where we did have the one size was big. We now have small, medium and large. But the sooner if we'd done that at the start, I think a lot of these comments about things being oversized or over-engineered wouldn't have happened to the same extent because things would have been more in balance. So yeah, that's a change I would make. Try and focus on where we can still use standard sizes, but go down one.
Yep.
More efficient rounding.
That makes sense. And then just in relation to quite a lot of carbon is a hot topic in the industry at the moment. It was just more of a question of, have you got as F&F any sort of carbon values for each of these steelwork masts in the range of Series 1?
Oh, now we've got values for the cantilevers. I know we're working on values for masts, but I don't think we have like a published table for different masts at the moment. No, but it's certainly something we've got my graduates working on at the moment, because I think carbon's becoming more expensive than pounds. More important than pounds, really. So it's where everybody's beginning to move, looking at how we can decarbonize as well as make price efficiencies. Okay. So yeah, not quite yet, but it's in process.
Keep me posted.
Yeah, will do.
Thanks.
And good examples where you, for the different sizes, where you can use a 250 mast with, say, a 10 mil, a 250 square mast for something, where originally they would have all been 350s. That's a big, just common sense, that's a big carbon saving going from a 350 to a 250. You must be saving about a third. And if you can use a 250, it's an absolute no-brainer to do that, isn't it? What people don't see is whether you've picked a 10 mil, a 12 mil, or a 16 mil wall thickness, they all look the same. So a 350 with a 10 mil wall still looks big, and yeah, it is physically big, but it isn't very heavy at all. And it's difficult to split what your eyes see versus what your brain knows.
Yeah, thanks, Rob. Right, there's another one here, unknown user. Would you have an idea of the size of the strut if you're applying the same load of high speed for high speed, so 30 kilonewton contact wire? Do you have an idea of what that would be?
Bigger.
Bigger, yes.
There's ifs and buts. I think the strut was 200, and I think we possibly had a large one that was a 220 or 240 square section. I must admit I can't remember. The driving factor was the length of it. So I think it's the size, the failure point, I think, is the square of the length, but linear to the tension. So doubling the tension doesn't double the size, but it depends what length you've got it across. So it's certainly going to go bigger. We've got calcs for what they can take. It would need a bit of thought for going to, say, 30 kilonewtons like HS2. Other things you could think about, that strut was made to be length adjustable from maybe 4 meters to 6 meters, top of my head. That adjustability also inherently brings in weakness. So if you're building something like HS2 that doesn't have the variability that Great Western had, we had level crossings, we had platforms, we had low bridges, everything had to be designed to be working on a 4.2 meter wire height and a 5.8 meter wire height, and with the embankments of sometimes the masts being down at the bottom. So if you're HS2 where everything's going to be a 4.7 wire or a 5.2 wire, whatever they pick, you could probably have a modular non-adjustable strut, and that would save a lot by
joined a
thinking
bloody
about that.
meeting, and everyone's
hi, sorry,
getting all
Bill, you've got your microphone on. Thank you. Sorry, Rob.
Yeah, if that makes sense, I would go away from the adjustability if you were looking at, say, HS2, and focus on standardization in that respect, so that you can probably get 90% of them would be the same. You could then pick a better steel size that would be perfect for your use to be efficient, whereas we were compromised by everything had to be adjustable. And adjustable meant fast construction, so again, we're big steel, but easy adjustability on site.
Come on. I'm gonna sit back down.
Do you know if you can mute that one, Simon? I don't think I can, because it's not my call.
No.
I'm not sure which one. I think that's
I think
Leanne.
it's Leanne Nichols,
Yeah.
so she's gone on mute now.
She's gone on mute.
Name and shame.
Hopefully she's not been attacked by the dog too much. Okay. Rob, are you still working on developing Series 1 into a UKMS 140?
So we are not. So UKMS 140, I think, exists by using the Series 1 technical drawings. I don't think the actual tech sheets are in UKMS. I must admit, I don't know. But like I said in the presentation, the monobooms, the TTCs, and the F boom, I believe, have been transferred into UKMS.
Yeah.
There was some talk of the SSAs. I don't know if they've gone in or not.
I don't know. Okay. There was a comment of a portal on for 2 tracks. I think that's when you put the photo up from Old Dolby. So I think that was just a test, wasn't it? That one. No, although it was in the range, it then went. Yeah.
That was when we realised that the one size fits all had to have more variance in it.
Yeah. Right. There was an unknown user. If this allows smaller piles where a set length of pile installed along the route, there are an area of a number of piles sticking out of the ground by 2 meters to this day in the Didcot area.
I've got no opinion. I don't know it. Yeah, I wasn't involved in the piling, I'm afraid. That the piling design changed a lot. They started using the Brinch-Hansen method, and then I think towards the end managed to get some efficiencies off that. And then I think they went to Ori. Some piles were left sticking out for good reasons. I
think there was a project management decision at one point just to go and stick in standard pile lengths at that en route section 3. So I think that's probably tied up there.
Yeah, there's that argument about high output, isn't there? If you're spending, I don't know, 3 hours designing a pile versus just make them all a metre longer and do them all the same, it's a lot quicker, but that's a lot of meters that you've got to pile, and there's a break-even balance somewhere, isn't there?
Yeah. Miguel has commented about some of the galvanizing wasn't very good, and they've took them 10 minutes. I think that's probably down to speed of fabrication. And
sorry, some of the galvanizing wasn't very good. And what?
Yeah,
Sorry.
yes, I will try to explain. When I was involved during the nights on installation of the TTCs, you said that it's taking less than 10 minutes. I can prove you that it takes more than 30, because most of the time the galvanize was not good. The pin didn't fix very, very well. And I remember leaving some TTCs over the ground and coming back home without installing them. Also, the efficiencies, the maximum I can achieve in section 1 and 3 was 7 per night, not during the weekend, midweek. So this is what why I have included the comment, just to express my experience. Thank you.
No one fed back up to us to make the pins smaller, and I guess you need to talk to your galvanizer if they're putting too much galv on. I think with the large TTC, that had a bigger pin, and that was a 50mm pin. I think we had some issues around that, where that perhaps started as a 52, and we reduced it to 50 because there were some issues around fit. But there shouldn't be many of those around.
Yeah. Okay, thank you. Then, I'm sorry, another unknown user. Now that Series 1 style steelwork can be allocated as part of UKMS, has any updating of the allocation tables to allow for UKMS tensions being considered?
Not by me, so I'm not responsible for UKMS.
No.
No, I appreciate that. Sorry, this was my question. I was more getting at, different SPS, different tensions. I don't know if the industry as a whole has ever considered reproducing, because I think, as you say, those allocation tables made choosing steelwork easier. We don't now
but
have
just
the
for
same.
Series 1.
Well, exactly, yeah.
Yeah. Obviously, you could use the Series 1 values for UKMS, and it would be safe, but it's not very efficient. I know Network Rail issued, I'm going to say last year, a UKMS civils manual. I don't know whether that included it or not. It certainly, if it hasn't been done, it would be interesting to have. It's certainly something we could do. Offering extra work isn't the reason I'm here, but we found those tables very useful. If you had a 11.11 version or a 15.12 version, it would allow quicker allocation, I think.
Right. I was just wondering if anyone had ever approached you about it. This looks like
nobody has. No.
Okay. Someone had a summary of it's cheaper and faster to put the big stuff above the ground than below, which is probably where you've been going with your presentation.
Exactly that. Yes. Thank you very much. Please tell your friends.
Yes. Okay. An unknown user also commented that I've never said that, so I think that's Mr. Skinner. And I've seen that presentation, Simon, so you're not getting away from that. All right, I'm going to turn it over. Gary has got your hand up. You've been sitting there quite patiently. Do you want to go come off mute and ask your question while I just sort out some of the other ones, please?
Yeah, thanks, Simon. Thanks, Rob. Excellent presentation as always. I don't want to be the guy who says it's more of a comment than the question, so I'll try and frame it as a question. With everything you said, stepping back from the detail a moment, looking at all the decisions being made in parallel, procurement that procured the wrong things, is to what extent are these all symptoms of treating electrification as a race against an arbitrary deadline, rather than a sort of production engineering approach of just, build a bit and learn, and then build some more and then learn and refine and marginal gains and all that sort of approach?
I think you've answered your own question, Gary. But yeah, the start of Great Western, for understandable and good reasons, was a bit of a scramble to get things done, and the priority was get things done rather than get things optimized. Towards the end of Great Western, the teams that were building, top of my head, out Bristol and into Wales, were really, really efficient. They knew what they were doing. They'd had practice. It was consistent behaviours, consistent people. They were just quietly getting on with it. Dare I say, rolling program. I don't need to preach to the converted. if you have the right number of people with the right skill sets, slowly chipping away or quickly chipping away, whatever team you've built, 100%, I think that's the most efficient way to do it. Don't make your changes in the middle of the project. Decide what you're doing, set your remit, plod away and do it. And Series 1, I think, or Great Western, was that victim of there'd been nothing much done for 10 years, and then we hit it really hard with a lot of electrification. We've now learned a lot of that. You look at Scotland. Scotland is just quietly getting on with it, and doing quite a bit of electrification, and they're busy doing the prep now to connect to the grid to get the power supplies in for future electrification. Just quietly getting on with it. I think that's the trick. Rolling program, quietly getting on with it.
Thanks, Rob. Agreed.
Yeah. Tim Evans, you've got a couple of questions. Would you like to come off?
Sorry, Simon, I think that quietly getting on with it is going to save you a lot more than what structure you've picked. It's management, not engineering. It's just quietly getting on with it.
Yeah, I was going to leave you and Gary in your own converted bubble and move on to. So if Tim would like to, if you're still on chat, would you like to come off mute and ask you've got a couple of questions? I see.
Yeah, I think you probably answered the first one, but obviously you've told us what went wrong. Those later phases where they were installing it, do you know what the run rate was in terms of installation costs compared to the start?
I've got no idea. That run rate at the start was not installation. That was the project overheads. So that was office people within Network Rail and externally. That wasn't the on-track costs.
I just wondered how. Yeah, it was more how more efficient the installation was once you got running and you knew what you were doing compared to the earlier stages. Was there you said it there that it was a lot better?
No, I don't have the hard numbers, but what I could see was there were fewer mistakes, there were fewer silly questions, there was less rework. It was just getting on with it.
Yeah, as you say, it comes back to the nice steady state of rolling program, doesn't it? Yeah. And the other one, obviously, the system's been up now. How reliable is it being compared to the other systems?
So I'm hoping Richard Stainton might be on the call. I can't see everybody.
I was going to say, on West of England PWI section, we've actually had Daryl Tiddy come on and discuss the reliability of the Series 1 system. And it seems to have been a bit of a presently they're seeing it's a bit of a bathtub curve. So initially there were some issues as a result of
there were a few failed insulators, weren't there, early days, manufacturing defects and things.
Yeah, but now presently, Tim, it seemed to be quite performing very well. And one of the big benefits that they'd seen as a RAM team, sorry if Daryl's on and I'm taking words out of his mouth, is the reduced electrical clearance requirements of Series 1 compared to other ones with regard to vegetation. I can send you the presentation that he did probably 6 to 9 months ago if you'd be interested. Sorry, Rob.
That's all right.
Yeah.
I don't have a hard answer, but I was talking to Network Rail STE a few weeks ago, and they did have the hard data, and they're measuring reliability in terms of delay causing incidents per kilowatt hour or megawatt hour that the infrastructure provides. And Series 1 was at the top of the most reliable by a long way. But I forget, whether that was one incident per 10 megawatts or 1,000 megawatts. I've got no idea. But yeah, Series 1 was the top of the tree, probably bailing out the Great Western inner, the fuse section on the first 10 miles. Is probably helping to keep Great Western not as bad as it would be.
Thanks very much.
Okay, there's another one from an unknown user. The structure allocation tables that were for quicker, simpler designs. Were there any thoughts on providing a simple spreadsheet calc tool for inputs, outputs? This would then allow for using reduced span lengths rather than using maximum span lengths only.
It was discussed, and we all felt a little bit nervous about giving out spreadsheet tools because everybody who's received somebody else's spreadsheet tool always fiddles, and they fiddle for the right reason. But the moment that tool has, say, my name on it, but somebody else changes it, they're going to say, well, I used Rob's tool and something's wrong. We would feel that we got the liability, but not the benefit. So we didn't want to give any unlocked tools out. I realise you could lock them, but people always want to adjust things. So that decision was had, but the corporate decision with us and Network Rail was to give out the tables. People were free to make their own versions if they wanted, but no, we'd stuck with just those tables.
Okay, thanks. Was much done on public engagement when putting structures through near residential areas did you use any different mast size to reduce the impact of a permanent object? But I think that's
So
down more to
I had no
regulation.
involvement in that. So my role was to design these structures that were rapid to install and all the benefits I've just discussed. There was no hard rule as to who had to put what where from an aesthetic point of view. Our view was, the guidance was, you should try and be consistent. So you shouldn't have tall mast, short mast, tall mast, short mast. You should just make them all cosmetically look about the same height. It just makes your eye see it as deliberate rather than haphazard. I realise real life gets in the way and project boundaries get in the way and things, but no, I in terms of what goes where, that's the allocation of the Series 1 structures. That's where people choose to put them, and we weren't involved in that side of it.
Simon, I think I can help answer that one. Yeah. As we were responsible for around 50% of the mast allocation. The simple answer is no. It was only where we had a statutory obligation to consult with, say, English Heritage, listed viaducts and places like that we did anything that stepped away from Series 1. Other than that, we always allocated the correct mast for the scenario, unless we were asked to use a bigger mast because it was sitting in a field somewhere, going to waste otherwise.
I think it's probably a good lesson for Great Western, isn't it? A little bit more public engagement would have got people along with them on some of the decisions made.
Yeah. And Gary, I think you actually covered the next question, which was, what challenge did the project have designing acceptable OLE over adjacent stroke listed structures? So I think that was more of an allocation Great Western question than a Series 1.
Yeah, they weren't Series 1. They were.
I'd say listed viaducts a fairly significant challenge, but we got through it. So Molesford and Gatehampton viaducts, and there are ones further west as well that used tubular masts, which were bespoke. The really big challenge was the World Heritage Site at Bath, where we were doing a lot of work on bespoke monobooms and bespoke TTCs, which would fit in with the Sydney Gardens better. But of course, that section famously then got cancelled, so that work was never completed, sadly.
Something I remember, Gary, talking about Sydney Gardens, we were on some of the early panels for that, and a lot of people were doing that assertiveness technique of saying what Brunel would have wanted was, and then saying what they wanted. And you can argue Brunel or they might want the most slender, non-intrusive visually thing they possibly could, or you could argue to go for something sort of clean and bold and modern. You can argue either, but none of us are competent to say what Brunel would have wanted.
Rob, is this the same Brunel who was putting massive timber viaducts all the way through Cornwall?
I suspect so.
Yes.
But yeah, that was a good lesson. We shouldn't just say what other people want. We should ask them and see what they actually want.
Yeah, someone who's just commented Brunel would have wanted the most complex and unusual thing that he could think of. So yeah.
I'm not going to comment on what Brunel would have wanted for the reasons I just gave.
Yes. Okay.
I haven't met the guy.
Yeah. There was also a query about for branches of Great Western Main Line where speeds were never going to exceed 100 miles an hour, for example, Didcot, Oxford. Were ever discussions during GWEP to offer a lower tension version? I think that's more of a project question rather than
there were some discussions, weren't there? But it was that mindset of high output, one system, one size fits all. Just build it all the same, so everybody has got the skill set. They're building it the same way. The maintainer has it all the same. Yeah. You can argue all day long whether you want 1111 on the branch lines. I see that side of it as well. It's a client decision, isn't it? How they want to balance construction versus maintenance versus risks.
Yeah. Absolutely, yeah, and that maintainability and that spares list is quite important.
Yeah. You could really easily go 1111 and keep everything else the same, but then your structures are over-engineered if you go 1111. But you're looking at what's the cost to redo the charts for the structures just for a small branch line. It might be easier not to bother. It's a cost-benefit study, isn't it? Someone needs to do.
Yeah. Okay. Richard Wales, you've got your hand up. Would you like to come off mute and ask your question?
Excellent presentation.
Oh, has he just vanished?
Sounds like the line just dropped.
Yeah.
I presume he wanted to say more of an excellent presentation, which has been
I assume so, yeah.
Which has been an overriding theme from many people on it. I don't know if Richard's come back. No. Okay. Right. I think Richard might get in contact with you separately, Rob. I think you've
Funnily,
got...
he's on my list of people to speak to about something else altogether today. So yeah, I'm sure.
There you go. Okay. I think generally I've come to the end of the questions. There was obviously some comments about speeds in chat as well. I've left that
Sorry, I'm not
separately.
looking at the chat myself.
No. We've had a very good high number of people. I think we maxed out at somewhere like 375 people. So well done, Rob.
Wow.
Thank you very much.
Thank you everyone for joining.
Yes.
You can find me through the Furrow and Fray website or with gb@furrowfray.co.uk. If anyone has any questions, happy to discuss.
Absolutely. And if you have any further questions, want to ask the speaker, there's also the PWI LinkedIn page that you could get in contact with us that way. Other than that, there's obviously the lunch and learn sessions coming up on the 19th of March for predictive maintenance, as I discussed at the start, and on the 16th of April, inserting structures under main lines using rails and jacking systems, a European practice. But other than that, I'm going to call the meeting to an end and say thank you very much, Rob. You very much deserve
You're welcome.
to go and get a very nice sandwich or something for lunch. Thank you everyone else for your time and engaging with Rob and the presentation. If we can all put our hands together and say thank you very much.